All right, stats. So I waited in my mind and decided that I want to teach section 10.2 and 10.3 at the same time. Overall, these are probably two of the easier tests to run on the calculator because they're actually run identically. You plug them in exactly the same way. You interpret the numbers that the calculator gives you the exact same way. The only difference is when you make your final conclusion and when you're writing your hypotheses, you base your answers off of those. So realistically, this is kind of like doing the same section twice with just some minor little differences. Now, because of that, I don't feel like giving you a quiz over section 2 and then giving you another one after section 3 is going to be very valuable. So what I'd like to do instead is ask you to just do section 2 during week 3. Make sure you keep up with the questions. When I put out the video for section 2, make sure you watch that video and go over it. But I will not be giving you a quiz after section 2. Instead, after week 4, I'm going to give you a quiz over both sections 2 and 3. Because honestly, the main challenge after learning both section 2 and section 3 is simply making sure that you use the right test in the right scenario. And so if you separate these two sections, it kind of eliminates the only thing that makes them challenging. And I don't want to do that. So anyway, guys, I'm going to teach you both sections in this same video. That means that for week 3 here, you can watch the video up to the halfway point if you feel like it, or watch the whole video and just keep in mind that there will be no new video in week 4. I will release 2 separate videos going over the questions from section 2 and the questions from section 3 though, so those will not be combined. All right, so we're still working with chi-squared tests, and that means you should know that there's still more than 2 outcomes to look at. But here's the difference. What happens if instead of just looking at one variable, like the side on a die, what if we have multiple outcomes and multiple variables? So the first example they want us to look at here, it deals with paper towels. Now, of course, these are made up because look at those brand names. Those are just ridiculous. We have wipe ups, wipe its, wipe outs. That's just silly. And anyway, the thing they're comparing is how much they either break or don't break under this usage that they're doing. They're dropping a golf ball onto a paper towel. So not exactly a real world scenario, but they're testing durability. Okay? And so there's 3 brands, and there are 2 things that we're testing, whether they break, yes, or whether they don't break, no. Now, this just as easily could have been a goodness of fit test, where we could say that the distribution of towels that should break under this scenario is this, this, and this. But instead, they've done a comparison of the yeses to the nos with the 3 different brands. Probably not my favorite first example, but at least it does it. Now, what we're going to be doing is we're going to be performing what's called a test of homogeneity. And a test of homogeneity is a lot like a goodness of fit in its idea. There is going to be a breakdown of results that are expected based on these variables and this data. We are going to see if the results are what we expect them to be. And just like in a goodness of fit, there's a huge limitation. We can't really point out that a specific result is the issue because anytime we run the test, we're testing to see whether the results are homogeneous, meaning that they are what we expect them to be, or whether the results are not homogeneous, which really just means that at least one of the things is not falling in line with the rest. Now, you can choose either one of the things to compare. So I could choose breakage to compare, or I could use brands to compare. Well, logically, I think it makes more sense to compare the brands. Now, you will notice in that table that they chose 25 paper towels from each brand. That means that they chose multiple samples, plural. That's really important because the main difference between the test we're running in this section and the test we will run in the next section is how the information was gathered. If the information is gathered by taking multiple samples, then you're using this test called a chi-square test of homogeneity. If you get one large group and then simply categorize them by multiple variables, then you would be running a test of independence, and that's in section 3. So technically speaking, if somebody would have went to a grocery store and just arbitrarily grabbed a bunch of paper towels and threw them all in their cart and then came and said, hey, let's test and see how durable these paper towels are. What we could do is we could start pulling them out of the bags and we could be like, all right, what brand is this? And let's assume that there were only these 3 ridiculous brand names: Wipe Ups, Wipe Its, and Wipe Outs. Okay? But then let's say that there's another variable, not just breakage, but something like, let's go with number of sheets of paper. Okay? So we don't just want to compare the brand, but we want to compare how many sheets comes on each roll. All right? So we'll have brand as one thing, and we'll have the number of sheets on a paper towel roll as another thing. That would be me categorizing one large group of data, which was just a ton of rolls of paper towels, into 2 broad categories: what brand they were and how many pieces of paper were on each roll. And that would be different than what you do in the test in this section, where you take multiple samples, you specifically separate them by one of their variables, and then test another variable, in this case, breakage. Okay? So keep in mind, homogeneity, multiple, random, samples, independence, one large random sample. That's the difference. All right, so how are we going to input this data then into the calculator? What am I actually going to do? Let's take a look. I want you to notice that in the chart, there are 2 lighter colored rows followed by a very dark row. And then in the columns, you have the 3 lighter colored portions towards the top and the very dark right side column. That's because the totals have been made darker than the actual data that was gathered. You do not, emphasis on the word not, need to plug in the totals. Please do not plug in the totals, or you're going to be getting every one of these questions wrong, and you might wonder why. So I only care about the data that's in the lighter colored boxes. All right? Here's what you're going to do. You're going to go to your calculator, and you're going to get to the matrix menu. Now you can see I'm already there, and some of you are probably thinking, where is that? So if I go back to the home screen, you access the matrix menu by hitting second, and then if you look at the inverse key just to the left of sign, you can see it says matrix. So if I tap that key, it's going to take me to the matrix menu. You don't want the names. You don't want the math. That's mostly stuff you would have done with matrices. You want to come over here to edit. Now, if you've ever inserted information into a matrix on your calculator and you've never deleted or reset your memory, you're likely going to see some numbers in some of those matrices. You can't delete them, at least not that I know of, without clearing it out. So don't worry about it. You can completely ignore it. And even if there's data in them, I promise, as long as you don't tell it to use that data, it's not going to hurt anything. So if you've never used your matrix menu before, then all of those might have no numbers written next to them, like my B, my C, my D, etc. looks. But I'm going to choose A. And what I'm going to do is I'm going to do a 2-row, because rows come first, by 3 columns matrix. And I've inserted in all that paper towel data. Okay? Now I'm going to come back to the textbook. If I scroll down, they talk about making a table. They talk about what the values in the table are called. You can read all that if you'd like. I'm not worried about it. They also talk about a new type of chart that they're very interested in when it comes to this data called a stacked bar chart. Now, I think they're neat and all, but unfortunately, with the limitations we have, with me not being in the ability to kind of talk to you guys and see you and work with you, we're going to skip it. We're not going to go into the stacked bar charts, so don't feel too bad about that. Okay? They talk about computing the values, and specifically they talk about how we would get the expected values. Now, for goodness of fit, it probably didn't seem terribly complicated. All we had to do was take the entire total number and divide by what we expected the result to be. But for this homogeneity test, and in the next section for the test of independence, there's actually a little bit of a formula for calculating the expected frequencies. You are supposed to take, let's look at the box, the row total times the column total divided by the grand total. And they've done that for us. And you can see that all those data points are now in the boxes. If you ignore the work that's happening, you can see that the expected values are 12.8, 7.2, 10, etc., etc. Okay? Now, that means that the expected values need to go in a different matrix, right? Kind of. So I had a student discover in my second year of teaching, and it was one of those things where I almost lost my mind afterwards because I had literally never seen this done before, that computing the expected frequencies is unnecessary. Now, I want you to pretend that we are not running the test yet, but we're going to run the test. I know that sounds silly. We're going to press Stat. You're going to go over to the test menu. You're going to scroll way down to the bottom of your list. And this time we're going to be choosing option C, the one that just says chi-square test. This can be a chi-squared test for homogeneity or a chi-squared test of independence. Now, we did put the observed values from those paper towels in matrix A. It's prompting you for what you want it to use. You have to use a matrix. The expected values. Now, I always thought before I started teaching that this is where they wanted you to say, where'd you put your expected values? I assumed you had to calculate them, put them in a matrix, and put it in here. I had a student who, again, this was my second year of teaching, so I went a whole year of teaching. I went through all of college and never knew this. And the student asked me, Mr. Ryan, why are you putting those in? And I was kind of just like, well, you have to have your expected values. He said, I never put in my expected values. And I was like, well, that's going to be a problem. You have to have expected values or it's going to give you an error. And he goes, no, it doesn't give me an error. He's like, I always get the same answer you do. Okay. So I'm going to come down and I'm going to press calculate, and no, the calculator is not going to give me an error. It's actually going to give me a result. And I thought, well, that's odd. Well, hold on. Now, if I hit second, and if I hit the inverse key, again to the left of sign, to go into the matrix menu, you will all of a sudden see that there is now data in matrix B. And if you come down here, and you have to go over to edit first, but if you come down to matrix B and hit enter, the calculator actually put in all of the expected values. And you might be thinking, the calculator was able to put in all of those expected values. Very interesting. Yes, I would agree, very interesting. Except, if you take a look here, it says that based on our results, and where are the results the same? 18, 7, 5, 14, 45. Okay, so you can see here that unfortunately I just realized that the data here on this example is not the same as the data in this second example. So I don't know why they went and changed them on us, but you can see here that they do not have equal sample sizes in this second data. So when I showed you guys the expected values, it was based on this box that's currently on the screen right here. And what we just did is based on the first example right here. So please keep that in mind. I know some of you are literally saying to yourself, wait a minute, those were not the same numbers he just showed us. And there's a reason why. So I don't know why, but they went and changed the values on us. They didn't need to do that. It is what it is. But anyway, it will get the values for you. You do not have to actually type in all of this information. So basically everything on this page here, you can ignore, because if you type it in on the calculator, it will do it for you. Now, if I go back, I have my expected values. I could pretend that I did those on my own. Obviously, I didn't. We can go back to the home screen and we can see what the results were from the test, which I guess I hit clear and I didn't realize that. So let me run that test again real quick. And this is why I say this will not really take you too long, because there's just not much information on the screen to analyze. You have a test statistic, you have a p-value, and you analyze that p-value. This is a very, very small p-value. It would be statistically significant. Okay? So let's talk about what we do when we run this test and how we are to write our interpretations. So in a chi-squared test of homogeneity, the first bullet point is by far the most important. You need independent, random samples of a fixed size. Notice they say they don't have to be equal, but you have to decide upon starting the test what they're going to be. Like if I was going to get a opinion type question from students at Clinton Massie who actually attend Clinton Massie, I might not want to get 25 students from each grade level, because that would be an overrepresentation of the juniors and seniors. The juniors and seniors tend to be much smaller in terms of attending the school, so I might want to get 25 freshmen, 25 sophomores, but then maybe I only want to get like 15 juniors and 15 seniors, so that those values seem a little bit more proportional. Okay? Now, you don't even have to make them all proportional. That's a good idea, but you just need to make sure that you're taking random samples of a fixed size, a decided upon value before you start. And the second part's really important, from 2 or more populations. It can't just be you took a random sample from one population and then decided to categorize them. Don't do that. Every outcome still has to have non-overlapping values. So you need to make sure that the things that you're testing don't overlap each other. If they do, you can't be running this test on it. And the expected values all need to be at least 5. So you probably need to run the test, check your expected values, and then go back and finish your analysis. Because technically speaking, the easiest way for you guys to check your expected frequencies is going to be to run the test so it fills in matrix B for you. You could do it by hand, but like I said, it's so much easier to do it that way. So what will the null hypothesis be? And I like to say something along the lines of the distribution of values for each blank, and you pick one of the variables, is the same for all. So basically, if I'm talking about those paper towels, I can say the distribution of paper towels breaking is the same for all 3 brands. Okay? And then the alternative hypothesis would be that for at least one of the brands of paper towels, the distribution of paper towels breaking is not the same across all of them. Okay? So basically, you always want to pick one of the variables, and you want to say that the distribution of the other variable is the same across all of them. And for your alternative, you would want to say that in at least one of them, the distribution will not be the same as the others. Then you'll get your test statistic, and you'll get your p-value, and you'll determine if the result is statistically significant or not. If it is, you have evidence to support that at least one of the things is not equal to the others, and if you get a result that's not statistically significant, then basically you just have evidence that says that the 3 or 4 or 5 or however many things there were are about the same across all of them. So if I would have got a result that was not statistically significant, I could say the proportion of paper towels that breaks is approximately the same for all brands. Okay? Pretty easy. So we're not going to do this next example, but if you wanted to see it, it wanted to ask people if they thought having kids was a necessary part of their culture, basically. And so you have people who decided that either, yes, having children was necessary, or having children is unnecessary, or they really just don't know. So they're basically taking fixed samples of people from each of these 5 countries. And so what I could do here is I could say, all right, let's run a test to determine if the distribution of responses is the same across all 5 countries. That's what my test would run. And so I would plug in those numbers and see if the result was statistically significant. I think you can tell at glance by looking at the numbers. US and Germany, yeah, they're pretty close. I bet that might not be statistically significant. Canada's not way different. Mexico and Canada are pretty close, so yeah, those are different than US and Germany, but not terribly different. But then you see India and you realize that, yeah, I bet this result is statistically significant. Their distribution of responses just looks way, way different than the rest of the countries. And not surprisingly, if you were to run this test, you can see that they got a test statistic of 628. That gave them a p-value that is so small, look at it on the calculator, it was more than 100 digits of zero before a sig fig, which means that the calculator actually displayed a p-value of 0. It is saying that if you thought that the distribution of responses across all of these countries was the same, that's impossible based on the results that were gotten. So not surprisingly, you end up with statistically significant results when testing homogeneity a lot, because homogeneity is literally testing to see if the distribution of answers is the same across every one of the things that you're testing. And the more things you test, the more likely you're going to have at least one of the things not fit the trend of the rest of them. That's why this test just really isn't like a full-blown test. You do it and you're done. Like I said, much like goodness of fit, it's step one in seeing that there's a problem, and then you move on to much more deeper analysis. So that is the test of homogeneity. Multiple random samples where you're checking to see if the distributions are about the same across one of the variables. So the questions I want you to work on in this section, there are only 2 questions I'm going to ask you to do. On page 707, you're going to do question number 17, and then you're going to do question number 21. So that's 17 and 21 on page 707. That's it. Now, let us go ahead, even though some of you might be like, oh, that was enough. If you feel like being done for the week, go ahead and pause me, come back to me in the final part of this video for next week. For those of you that want to keep plugging along, let's look at independence. There is only one major difference between a chi-squared test of homogeneity and a chi-squared test of independence. And if you look, you're just going to take a random sample from one large population. So instead of independent random samples, it's a random sample from one large population. That's it. Then you still need to make sure that everything falls into one category, no overlapping categories. The expected values need to be at least 5. These will be plugged into a matrix just like homogeneity. It will not look different. And I think this is probably going to be your guys' favorite part of all the tests we've done. Every single one of the hypotheses is written the same way for this test. When you are conducting a chi-squared test of independence for the null hypothesis, you will say that variable 1 is independent of variable 2. So if I go back to my example of paper towels and how many sheets of paper are on them, I would just simply say, for my null hypothesis, that the number of sheets of paper on a roll of paper towels is independent from the brand of paper towel. And then the alternative hypothesis is that the two things are not independent. That's it. So I would just simply say that the number of pieces of paper on a roll of paper towels is not independent to the brand of paper towel. It is as simple as that. You'll get a test statistic and a p-value by plugging the numbers in, pressing enter, and interpreting the result. And not only are the hypotheses easy, but the conclusion is also really easy. If the result is statistically significant, then all you have to do is state that the one variable is not independent of the other variable. And if you get a result that is not statistically significant, then you're going to say that the two variables are independent, or at least that the evidence supports that. So you can see there's another type of chart that they really enjoy on this one. These right here are called column charts, and I kid you not, one of the actual questions in the assignments in the past has asked students to draw one of those. Unless you guys are the most artistic human beings on the planet, most of us, including myself, if somebody said, hey, I need you to make a column chart by hand, I would just stare at them blankly like you're kidding, right? Those are crazy. So on a computer, that looks really pretty, kind of neat to analyze. I hate the fact that some of the bars are hidden behind others. Kind of feels like that defeats the purpose. But nonetheless, neat. That's what they look like. You will not need to make one by hand, obviously. That's pretty crazy. So sadly, the only good question I actually like is this one, and there's a lot of stuff happening. So let's read. They took a random sample of 5,387 Scottish children. That's one large random sample. They then categorized these children by their hair color and their eye color. Now, if you're like me and are going to want to debate on why the categories are as weird as they are, that's a question for another time. But hair color was classified by the following categories: fair, red, medium, dark, black. Again, feel how you will about those categories. Eye color was classified as blue, light, medium, dark. I feel like somebody was mixing up hair color, eye color, and like the cook on a chicken. But no, I guess these are our categories for hair color and eye color. So just to show you guys how simple this would go, if I said perform a test to see if there's an association between these two variables, you would say, hey, this was one random sample. I'm going to do a chi-squared test of independence. You would then say it was a random sample. Check. I guess none of these are overlapping categories, even though the categories are very odd. And after you plug in all this information into your matrix, you would check to see that the expected values are all at least 5. They will be FYI. And then after you plug all this information in, you would say that your null hypothesis is that the hair color and eye color of Scottish children are independent. Your alternative hypothesis would be that hair color and eye color of Scottish children are not independent. And then you would calculate the data. You can see that if you thought the last test statistic was crazy, here comes an even crazier one. We just got a chi-squared value of 1,240. That's a huge test statistic, and not surprisingly, giving us a p-value that has more than 100 digits of zero. So yeah, this, much like the previous example, just simply says, no, these two things are clearly not independent. This was a statistically significant result. You reject the null hypothesis. You have definitive evidence to prove that these two variables are not independent of each other. Okay? So I hope you guys can see that these are not a whole lot different than the chi-squared test of homogeneity. All you need to do to get started is read about how the information was gathered. Did they get multiple random samples and then look at a variable? That's homogeneity. Or did they get one large random sample and look at two variables? That's independence. But both tests are conducted the same way. You type them into the matrices on your calculator. You do not need to find the expected values. You just need to run the test and then interpret the results. So guys, that's it for this section. This one went pretty fast, I think you noticed. I love the fact that there's a nice little debate starting here on this page where it talks about homogeneity versus independence. That is definitely worth a read if you have not done so. Okay, so please keep that in mind. And of course, there's some other information about stuff that we're just not going to go into as much detail in. All right, so the questions that are for the third section, and that should be week 4 by now if you are working on these, are on page 704 726. Okay, 726. And what I want you to do is I want you to start with number 35. So that's question number 35. There's just a tiny little paragraph here on the first page, but most of it is on the second page. Okay, so question 35 is the one question I want you to do. And then the other question I want you to do is number 37. So that's E35 and E37. Those are the only two questions I want you to do. And those questions start on page 726. Keep in mind, though, that there's barely any of the question on 726. So most of it is on 727. So the answers to those questions will be in a separate video. You will take a quiz over both sections 2 and 3 at the end of week 4. So anyway, guys, I hope that this chapter hasn't been completely overwhelming. Hopefully you've been emailing me with your questions if you've had them. I look forward to possibly seeing you guys at school if we haven't gotten an update. But if not, we'll keep plugging along with Chapter 11 next week. I will talk to you guys then.